So now we know with flow control. Now the next issue is error control. Error control has to do with what do we do if the packet is lost. So here's an example. We send the packet number 1, it is acknowledged. We send the packet number 2, it is not acknowledged. What do we do? Well, we set a timeout, and when the timeout triggers, we send the second copy of packet 2. That is a retransmission. Now it is quite possible that the packet makes it, but the acknowledgement doesn't. Same thing happens, it doesn't matter. So packet 3 makes it, the acknowledgement for 3 was lost, so then we time out and we send packet number 3 again. Another acknowledgement will be sent, and hopefully that will make it. Is that how do you calculate timeout? It would be smart to calculate the timeout based upon the round trip, right? So basically, when we get into TCP, every protocol has a different method of timeout. TCP has an algorithm which calculates the round trip, and then there's some safety measure, multiplies it with some number to get a timeout. Alright, so there are two methods. This is called stop and wait, because you send and you stop and wait, right? Again, another one is something similar to Windows, but in this case we call it ARQ. Another thing is we call it ARQ. ARQ stands for Automatic Repeat Request. Is that you automatically retransmit, right? So go back and ARQ. So the next method is that if you suppose you send 1, you send 0, you send 1, you send 2. When you send 2, the receiver is going to say, sorry, I did not get 1. That is called NAC1, negative acknowledgement for 1. The question is two-part. Question is, do you always send the NAC when you receive the next packet? The answer is, actually, some protocols don't even send NAC. So NAC is just shown in this picture, doesn't mean that we send it at all. So there are some protocols, they may not even send NAC at all. Alright? However, in TCP, when we come to TCP, what will happen is if you get 1 and you get a 0 and then you get a 2, you will send a message which says, I got 0. Alright? And so if you get twice the same message, suppose when it got a 0, it says I got 0, and then it got 2, it says I got 0. That can be interpreted as NAC1. When you got 2 I got zeros, then you know why you are getting 2 times, because something happened in between. Oh, every packet has a number. So remember sequence number? Every packet has a 3-bit sequence number, so it will say number 3 and then it will say number 3 again. Alright, so back to here. So if there is an acknowledgement, either way, either negative acknowledgement or because there is whatever it is, the question is, what do you send at this point? Do you send 1, 2 and 3? You have already sent 2 and 3 and you got the negative acknowledgement for 1. Now you have 2 choices. One choice is you resend everything after 1, including 1. Second option is that you just send 1 and then hopefully 2 and 3 will made it, and then you will get acknowledgement for 3. Right? If you choose this option where you send everything including 1, that is called go back N. That means I'm going to go back the whole thing and I'm going to retransmit everything, even though you just didn't get 1, but I'm going to send you 1, 2 and 3. This is called go back N. The other option is coming in the next slide, and the sender has to go back and retransmit all frames. The advantage of this method is that the receiver doesn't cache, doesn't store any of the packets which are not in order. So it got 0 which is in order, but 2 is not in order. 2 is out of order. Right? It gets 2, it throws it away, and it sends a NAC1. It gets 3, it throws it away and sends a NAC1. Alright? And then whenever one of those NACs reaches the sender sends 1, 2, 3, everything. So the receiver is simple. Receiver does not have to cache. Acknowledgement is always cumulative. What that means is, if I say I received 2, that means I have received everything up to 2.
Why?
Huh?
Why?
Okay. So the next upgrade is selective acknowledgement, which is little bit more complicated. Then I have to send you a bit map which says, okay, I received 0, I received 2, and I didn't receive 3, and then I received 4, and I didn't receive 5, so you have to send a bit map. That is also next extension. However, that is complicated enough that many people don't implement it. But so if suppose you don't have a normal acknowledgement, means it is cumulative. Okay, here at this point the sender knows that the receiver did not get 1, and therefore 2 and 3 it will not keep, because that is the understanding that the receiver will not cache out of order packets. So it's going to send all of that, and that is go back n. Hold on, right? You are saying selective acknowledgement is not that difficult. Is that what you're saying?
Yeah, I mean, why is it so?
Yeah, it's difficult, but that's all. You just take my word for it. In the sense that, here's the thing. Everything is becoming more and more complicated. So in the beginning, when the protocols were for a small speed, for small distances, for small window sizes, there was no need for selective acknowledgement. Today, when we talk about 10 gigabit speeds with windows of 1000, selective acknowledgement is worth it, right? But for a small number 2 and 3, who cares? We can send 2 more packets, right? So this is for the old days, yeah. 2 is out of order. You know why 2 is out of order?
No, it's not in that example.
Yeah, it is. So anything which is not expected is out of order.
Okay. All right.
Anything that is not expected is out of order. So here we were expecting 1, and we are getting 2. So 2 is out of order. Alright, we don't send packet number 1 through this way, and the packet number 2 that way, and packet number 1 through this way. I mean, again, you can do this. It's not, I mean, it's something long, but then somebody has to keep track of all the things at the end. The receiver has to, keep everything in place for out of order assembly, and the out of order is basically can cause some deadlocks and things like that. So we generally don't do it. Okay, right? Everybody saying go back and ARQ. Now the next option would be selective repeat. In selective repeat, you just send whatever is not acknowledged, and everything should be fine. So basically you got a negative acknowledgement for 1, you send 1, and then when permitted you send 4 and 5. Don't worry about 2 and 3. In this case, this works only when the receiver keeps out of order packets. And so you could negotiate when you start the connection, and it depends upon the protocol. If the protocol allows you, then you could negotiate that, okay, I'm going to cache out of order, so you should use selective repeat. Yeah.
So what if we don't care about packet 1 anymore? Do we still have to send it again after doing that?
Okay, so the thing is, this is error control. Error control means we care for every packet. If you have packets that you don't care for, you don't send through this protocol. Then you send through a protocol which is totally unreliable, has no acknowledgement, you just send it and forget. And there is a protocol like that. Anybody knows that protocol? UDP, right? That doesn't have any of this. But TCP, on the other hand, is a reliable protocol, and therefore every packet is acknowledged, so you care for every packet. Alright, this is also known as selective reject ARQ. So whether it is selective repeat or selective reject, same thing. Alright, now the window size. If your sequence number space is 0 through 7, and you are going to use selective repeat, then your window size cannot be more than 4. Your window size cannot be more than half of the number space. Let's see the example here. So here your number space is 0 through 7, right? You are doing mod 8. And therefore your window size cannot be more than 4 in this example. Reason is, suppose you send 0, 1 through 4, 5, 6, 7, and the acknowledgement for 7 did not make it, right? And then you send 0 because you got the acknowledgement for 6 before, so you are going to send 0. If you send 0, then so what I said was wrong, that you acknowledgement for 6. Suppose you didn't get any acknowledgement and then you happen to have sent 0 because your window was more than 8, then it will be very confusing for the receiver. So obviously your window cannot be more than the sequence number space, but in this example it cannot be more than half the space. So it cannot be more than 4, because if it is 5, then you can get into areas where the numbers are confusing. So where the numbers are confusing, this example doesn't really give that very clearly. So I have to make another example, which I will do next time, not today though. So basically, if you have 3-bit sequence numbers, the maximum window you can have is 2 bits, which is 2^4, and so on and so forth. Anyway, summary of this error control and flow control is this. With the stop and wait flow control, the U was 1 upon plus 1 plus 2 alpha. The window flow control, it was W upon 1 plus 2 alpha, 2 alpha plus 1. If you have P as the probability of error or packet error, then the numerator goes down to 1 minus P. So with the stop and wait ARQ, the throughput or efficiency is 1 minus P upon 1 plus 2 alpha. Instead of 1, you have 1 minus P, where P is the probability of loss. For go back N ARQ, here is the formula, which is 1 minus P upon 1 plus 2 alpha P, or W upon this and this, where if W is more than this and that, and select to repeat. So these formulas are extensions. We haven't derived them here, but these are extensions of these two formulas that we derived if P is the probability of error. So we have 3 formulas: stop and wait, go back N, and select to repeat. Right? With the stop and wait, the window is 1, so it doesn't really apply. The select to repeat and go back N formula should be exactly the same as stop and wait if W equal to 1. With W equal to 1, these two formulas would be same, and if you put W equal to 1, this and stop and wait would be same. Okay. The main thing is that again similar thing remains like before we saw. I think this is very similar to the previous one, is that as alpha goes up, the efficiency goes down, and here we have drawn these graphs for different values of W, and go back N and select to repeat. So now let us see. This is go back N and select to repeat. For N equal to 127, they are very close. For W equal to 7, they are almost overlapping. And for stop and wait, they are identical. Right? If your W is 1, then go back N is equal to select to repeat, right? That is trivial. If your W is 1, then select to repeat is same as go back N, is same as stop and wait. As the W becomes larger and larger, then the select to repeat helps. So select to repeat doesn't really help if window is small. Now that answers your question as to why we don't do select to repeat, because we were in this range here. Right? Now as the networks are becoming faster and faster, we need bigger and bigger windows, and when we use the windows of 1000, then it does make a difference. That the selective repeat was not done before because the windows were not that big. Traditional windows, when I did my PhD thesis, at that time 8 was a large window. Now it is 8000. You know, the largest speed in my days was 1 megabit. Now it is, you already have 10 gigabit. So things have changed. So that finishes the transport layer design issues. The 5 key points of this particular module of chapter 3 is that you can do multiplexing and demultiplexing by a combination of source and destination IP address and port numbers. So you saw as to how the IP addresses and the port numbers are used, both source and destination, so that multiple people can access the same server at the same time and get the correct responses without any confusion. Let's say you want to do HTTP. What is the destination port number? 80. What is the source port number? Arbitrary. You could take any number. 3023 is a good number. All right. So that is important to remember. Port numbers have to be standard for the destination, but not standard for the source. Window flow control. Then we talk about that today, so you shouldn't have forgotten. Window flow control is better for long distance or high speed networks, which is what we have today. Longer the distance or higher the speed, larger the alpha and larger the window. Okay, now you should just put this in your brain. Basically, we keep this in our brain. In the sense that whenever we see a high speed network, that's what we are working on nowadays. Most of the time is high speed. We want to go from 10 gigabit to 100 gigabit to bigger and bigger, right? We need bigger and bigger windows. Stop and wait flow control is okay for short distance or low alpha. Again, as your alpha goes up, you need windows, and you need selective repeat. Selective repeat is not required if the alpha is small. Right? The window is small. So those are the conclusions. So as the propagation delay goes up, alpha goes up, things go down, everything else goes down, because basically everything means the efficiency goes down. Okay? So the long distance networks are tough to handle and the high speed networks are tough to handle. Alpha, okay? And so that brings us to the end of that.